Chapter 3 is entitled Chemical Reactions and Reaction Stoichiometry. For this portion, we're going to be focusing on chemical reactions, those chemical changes that we spoke of in Chapter 1, in which we see a substance or more than one substance or undergoing a change in chemical composition. Chemists use chemical equations in order to represent how chemical reactions take place. For example, carbon reacts with oxygen in order to form carbon dioxide. Carbon dioxide is a compound that is made up of carbon and oxygen. So one pathway to making carbon dioxide is combining carbon and oxygen. That is a chemical reaction. The chemical equation that speaks to that reaction would fall in a particular format. Now, chemical equations are represented with two components. There are the reactants and there are the products. Reactants are the starting materials and the products are the ending materials. One might go so far as to say that reactants react in order to produce products. So in the chemical reaction, that is carbon reacting with oxygen in order to form carbon dioxide, carbon and oxygen are the reactants, while carbon dioxide is the product. Now, a chemical equation is written, as I mentioned, kind of similar to a mathematical equation in which we have two sides. On one side we have reactants, on the other side we have products. In the middle we have an arrow, whereas with a mathematical equation we would have an equal sign, but with a chemical equation we have an arrow in order to indicate the direction of the reaction. And lastly, if we have multiple reactants or multiple products, they would be separated on either side of the equation by a plus, suggesting that carbon reacts with oxygen, or carbon plus oxygen would give rise to carbon dioxide. On the bottom of this slide, we see the equation that speaks to the formation of water from hydrogen and oxygen. If you'll remember, hydrogen and oxygen are both materials, both elements that exist in nature as diatomic molecules. So when hydrogen reacts with oxygen, it is the molecule of oxygen, the O2 molecule, that is going to react with molecules of hydrogen, the H2 molecule, in order to produce water. Now, in the previous slide, we showed how hydrogen reacts with oxygen in order to form or produce water. But hydrogen and oxygen can also combine in order to form hydrogen peroxide, a compound that is different than water. So in order to illustrate the difference between these two reactions, we're going to take a look at their chemical equations, and specifically the balanced chemical equation. Hydrogen peroxide is a compound with the chemical formula of H2O2. So we're in a moment going to take a look and see exactly what its chemical equation looks like in terms of its formation. Well, in the production of hydrogen peroxide, we see hydrogen in its diatomic form reacting with oxygen in its diatomic form in order to form hydrogen peroxide. And that is what we call a balanced equation. In order for an equation to be considered balanced, then we have to have the same elements on either side of the arrow, as well as the same number of atoms on both sides of the arrow. So in the first equation, the one that we see involving the production of hydrogen peroxide, on the left side of the equation, we find hydrogen and oxygen. On the right side of the equation, we find hydrogen and oxygen. And we find them in the same amounts. We find 2 atoms of hydrogen on the left, 2 atoms of hydrogen on the right, 2 atoms of oxygen on the left, 2 atoms of oxygen on the right. That represents a balanced chemical equation. In other words, if I take 1 molecule of hydrogen and 1 molecule of oxygen, then I can make 1 molecule of hydrogen peroxide. But let's take a look at the production of water. Now, the simple chemical equation shows us that hydrogen reacts with oxygen in order to form water. But upon closer inspection, we will find that this equation is not balanced. While we do have the same elements on either side of the equation, it should be noted that on the left-hand side of the equation, we see 2 atoms of oxygen in the diatomic oxygen molecule. While on the right-hand side, we only see 1 atom of oxygen tied up in the molecule of water. So 1 molecule of hydrogen does not react with 1 molecule of oxygen to make 1 molecule of water. This is not a balanced equation. In order to balance the equation, we need to know what elements we have and how many atoms of each element we have. So if we were to indeed balance this equation, we would need 2 atoms of oxygen on the right-hand side. So we account for that by suggesting 2 molecules of water. If each molecule of water has an atom of oxygen in it, then 2 molecules of water will have a total of 2 atoms of oxygen. So if we place the number 2 slightly to the left of the molecule of water, then in this equation it suggests the formation of 2 molecules of water, which would give us the appropriate amount of oxygen to balance out with our reactant side. Now, there's a problem. In doing so, we have thrown off our hydrogen count because 2 molecules of water have 4 atoms of hydrogen. So on the left-hand side of the equation, we only have 2 atoms of hydrogen in our diatomic molecule. In order to balance our hydrogens, then we need to place a 2 before the hydrogen molecule in order to bring us to a total of 4 atoms of hydrogen on the left-hand side. At the bottom of this slide, we see the balanced chemical equation that we saw on the previous slide and that we're going to see on the next slide for the production of water. 2 molecules of hydrogen react with 1 molecule of oxygen in order to produce 2 molecules of water. Here we see both of those equations represented together in a comparison to show that everything doesn't react in a one-to-one fashion. So even though we may have the same reactants, different amounts of reactants combined can result in different products being formed. It should be noted that when trying to balance an equation, we do not change the subscripts of a particular reactant or product. If you do that, then you are changing the identity of the compound. If the reaction is hydrogen reacts with oxygen in order to produce hydrogen peroxide, then those are the 3 things that must appear in the chemical equation. If you change any of those, then you are changing the reaction that is taking place. So the only thing that we can do when balancing a chemical equation is to add those numbers before each component, numbers known as coefficients, in order to speak to the number of molecules of a particular substance, whether it be a product or a reactant. Now, on the previous slide, you may have noticed some things in parentheses following each of our products and reactants. There are some symbols that we find in chemical equations that may be of importance. For example, one thing that we find in parentheses immediately following each substance is the state of matter that the reactant or the product can be found in. If we see a G in parentheses, then that means that reactant or product is in the gas phase. If there's an L, then that substance is in the liquid phase. If there's an S, that substance can be found in the solid phase. And if we find the letters AQ in parentheses, that suggests aqueous solution, or the idea that the substance in question, the component in the reaction, is dissolved in water. Another example of a symbol that might be found in a chemical reaction. If you look atop the arrow, that suggests the direction in which the reaction is proceeding. You'll see a tiny triangle. That triangle suggests that heat is being transferred as a result of this particular reaction. In order for methane gas, CH4, to react with oxygen in the gas phase, we need heat in order for this reaction to take place. If we combine those two things and we add heat, then we can see the production of carbon dioxide gas as well as water in its gaseous phase, or water vapor. There are a few types of reactions that I want us to be able to identify. We won't necessarily be able to predict the products of a reaction, maybe not just yet. But I do want us to be able to recognize reactions of a particular type when we see them. The three types of reactions that I want us to focus on are combination reactions, decomposition reactions, and combustion reactions. In a combination reaction, two or more reactants combine in order to form a single product. The table on the bottom of the slide suggests a series of combination reactions. In general, the form is A plus B produces C. All right, that's the general form. And underneath that, we see three different examples of combination reactions. Carbon in its solid form reacting with oxygen in its gaseous form in order to form carbon dioxide gas. Nitrogen in its gaseous form reacting with hydrogen in its gaseous form in order to form ammonia, a compound with the formula NH3, in its gas phase. And lastly, calcium oxide, a solid ionic compound, reacts with liquid water in order to form calcium hydroxide, a substance which is dissolved in water. You'll notice that each and every one of these equations has been balanced. So a combination reaction involves two or more reactants and only one product. A decomposition reaction can essentially be thought of as the reverse, where we see one reactant which is breaking down in order to form two or more substances. At the bottom of the slide, once again, we see a series of decomposition reactions. We see potassium chlorate decomposing in order to form potassium chloride and oxygen gas. Lead 2 carbonate decomposing in order to form lead 2 oxide and carbon dioxide. And lastly, copper 2 hydroxide decomposing in order to form copper 2 oxide and water. The image on the slide shows the releasing of an airbag. Well, inside that airbag, we see a compound known as sodium azide. And sodium azide undergoes a decomposition reaction very quickly in order to produce nitrogen gas, which then inflates the airbag. So, in summary, a decomposition reaction involves one reactant and two or more products. Now, a lot can be said about combustion reactions, but we're going to try and simplify it as best we can. Typically, combustion reactions are rapid reactions that produce a flame. Combustion reactions most often involve oxygen as a reactant combining with an additional reactant in order to form a product that involves that oxygen combination. In order to simplify things for our purposes, in order to be able to recognize a combustion reaction, we're going to speak of a combustion reaction as one in which we see a carbon and hydrogen containing compound reacting with oxygen in order to form carbon dioxide and water. So when looking at the three types of compounds, we have the combustion reaction, we have the decomposition reaction, and the combination reaction. Based on our discussion, we should be able to, simply by looking at an equation, determine which of these three types of reactions a reaction may be. And it may turn out that it's none of the above. There may be a reaction that doesn't fall into one of these three categories. There are many, many more types of reactions, but these are the only three that we're going to speak of at this particular time.